everyone. So my name is Ninh. I'm from school of Ninh, DCU. I just finished my PhD, and my research topic is about quantifying stress reduction in live log data using wearable sensors with high stress. So I would like to give you a brief introduction of how you can detect stress using wearable device, like for example this watch, like every wearable watch that you can have. So a little bit about my motivations. So as how to use that live log data can be divided into several types. So what we have in our system now is that we can exploit vision data, the location data, and also the activity data. So we include those data into our live log retrieval systems to search for the moments that you are interested in. However, the biometrics data is still in the raw format. There's no semantic meanings in those informations. And for the others, the data, for example, attention, hearing, and speech, they are rarely recorded. They can usually record it, but they rarely share to others because of some privacy concern. So for biometric data, some biometric data you can capture from your wearable device, including the skin response. There's another academic name is the electrodynamic activity, or the EDA. The second one is the blood volume pulse from PPG signal. This is from the infrared light in your wearable watch, in case that you notice. And the final one is the skin temperatures. This biometric data can also be referred to like the physiological response of the body. And those physiological data can be used to infer a lot of information about your emotion and your stress status. So how can we detect stress using those signals? I'd like to give you a brief introduction about the stress process. So in stress situations, we usually refer to in fight or flight situations. When you are stimulated by stresses, your personal moderators will automatically come to the appraisals, and we consider it might be a dangerous situation. It might be not a dangerous situations. However, in stress situations, the appraisal systems will resolve in three components. With these three responses, with this comprised of the affective response, which is what in your head, what you're thinking of the situations, how stress level you are. The stress level will reflect into your behavioral response, how you react to the situation, how you behave to others when you are in a fight. And finally, it will also resolve into the physiological response. So I would like to emphasize that this one, the physiological response, is the one that you cannot control yourself. So those response will look in the cycles, and I used to call it a stress response. And those stress response, in case of stress situations, it will affect both your mental health and your physical health. So the appraisal systems, the appraisal system that consider this stress and not stress, is controlled by the human nervous system. So the human nervous systems comprise of two components, which is the central nervous system. It contains the brain, and your spinal cord. And the second one is the peripheral nervous systems, which contain the nerves branching out from the spinal cord and extend all along your body. So the theory is like this. The peripheral nervous system is comprised of the autonomic nervous system and somatic nervous system. So in the fight or flight situations, you have two responses. The first one is the one that you're conscious. It's the behavioral response. You might react to or behave to reflect to the situation immediately. For example, you run away or you fight back to the situation. So it is controlled by the somatic nervous systems. I would like to call it is a voluntary response. So for the autonomic nervous systems, it is the involuntary response, which you cannot control by your body. It's unconscious, so it is automatically controlled by your body, so you cannot notice. So this one, the autonomic nervous system, could be divided into two component, which is the sympathetic division and the parasympathetic division. So the appraisal system that you see before is the autonomous nervous system, which automatically responds to stress situations automatically without your conscious brain. And this is what we try to capture, because we believe that you cannot control those reflections, so the response. So we try to capture, to provide some insights about how you reflect the stress. So the first signals that we use is the skin response. So for the definition, so it's variation of the electrical characteristic of the skin in response to the sweat secretions. So in stress situations, the autonomic nervous system will increase the activity of your sweat gland activities. So you can see that this is a raw, original skin response signals, and it can comprise of two small components, with the phasic one, the phasic component, and the stonic component. Here in the picture, you can only see the phasic component, and this is what we researchers are interested in, because if you look in the phasic signals, you can see that there are some fluctuation in the signals, which indicates that in those moments you are having some events. Your body is response to some events that you are facing. Another signals that we researchers use is the heart activities. So in some clinical, like some hospital, we usually record heart activity using ECG signals. So ECGs are electrocardiograms. It measures the heart's electrical activities via the electrode placed on your arms, the legs, and the chest. So in theory, the heart activity is considered as the most important features for stress reductions, as it's affected directly by the autonomic nervous systems. In stress situations, you can experience some fast beating, fluttering, or pouring heart. And in case that you notice when you come to hospital, when you're recording your heart activity using ECG, you can see that we usually call this the P-wave. P-wave comprises of many components, and the one that has most meaningful is the R peak. The peak here, the R peak here, because for example, when you do exercises or some heavy activities that will require you to many activities, for example, the R peak, the gap between the R peaks will be very short. This means that your heart is doing a lot of activities. In case of when you are resting, the gap between the R peak is longer, because your heart will slow down. So, however, you cannot capture the ECG signal using your wearable device. Another alternative method is using the blood volume pulse. So, it is the variation of the skin hole associated with concurrent change in the blood volume during the cardiac signals, and this is recorded using the PPG signals in most wearable devices. So, and you can see in these pictures, we are interested in the gap between the R peak, I would like to call it the interbeat interval, and it can be estimated using the PPG signals, where the gap between the systolic peak is inferred and then computed to estimate the interbeat intervals. And this interbeat interval is the one I mentioned, with the gap between the R peak that can indicate if your heart is working more or less. And finally is the skin temperature signals. So nowadays, the skin temperature's value can vary between 33 and 35 degrees Celsius. This is estimated based on the positions of your wearable device, for example, like wearable watch. And in theory, under stress conditions, your skin temperature will drop because of the reductions of the peripheral circulations. However, this is not always a reliable feature to use, because the skin temperature can be affected by the environment temperatures. However, it is still a valid feature. So, for stress sessions that I do in this experiment, so I use 4 stress assets, and and use the device which is called, in particular, infrared wristband. It captures this signal in real time. And most of the design of the experiment is stress control, comprised of the relaxed sessions and the stress sessions, where the stress sessions involve the people doing some cognitive tasks, load, driving around the cities, maybe some pretending, asking them to do some interview with a panel without their intention. So in constrained environment, where you control every conditions of a person during the experiment, we can build a model that predicted up to 96% accuracy of your stress level, of your stress moments. So I try to deploy it into a constrained environment within it's called live log data, where you capture the data in daily life. So I record with this one in my experiments, and this one I'm required to wear multiple wearable sensors during 6 days, 6 hours per day, and the photo is captured for every 20 seconds. And for the 3 users, the data in the lab-based experiment, the accuracy is around 88.58 to 100%, which is perfectly in the constrained environment. However, when it comes to the real life, it drops to 56% to 62%. It's because that there are many factors that you cannot control in your daily life. For example, if you just sitting still, but you have coffee, it can increase your heart rate, and you can mistake it because you can make a mistake because you might not be stressed, but your heart activity is still high, for example. So in perfect conditions, the user should not have some coffee or some caffeine when they want to measure the stress levels, for example. So this means that there still need a lot of research into this area. So in conclusion, the mental stress formation is valuable, and seamless stress detections can be achieved using machine learning models, which means that I can detect if you're stressed or not in real time for up to seconds. However, it is still a challenge to do stress detections in a constrained environment. And some future work is because my work is also only around detect if you're stressed or not, stress event. You can extend my work to detect different level of stress. For example, low stress, moderate stress, and high stress. And also you can do more research to enhance stress detection accuracy in live log data or in a constrained environment. And it is also good to know that those signals can be used to recognize your emotion. And many researchers is doing research on emotion detection and emotion recognition based on some physiological signals, heart activity, skin response, and also skin temperatures. And that's all. Thank you for listening.
So one thing was not clear to me, what is the source of truth for these data sets? How do you know whether the person was really in a stress situation or not?
Okay, that's a good question. Collecting stress data set is very challenging because you are not sure if a person is stressed or not. So for example, for benchmarking data set, WASAD, they usually assume that people are stressed during the stress sessions, where they have many factors during the stress sessions. For example, the surprise to the participant of the task, and the level of the difficult levels of the task also, and the rush of the task. So those also consider as a stress, the factor that can increase the stress level of a participant. Some data sets, they ask a person sitting next, for example, in a affected road where people are driving around the city. There's a person sitting next to the driver, and try to, based on their response, measuring the stress levels from 0 to 1. And then after that, the driver will look back into the videos that we recorded during the driving, and to see, compared with the evaluation of that researchers, to validate if this is correct stress level or not. But it's still subjective. And for my experiment, I usually ask the participants to record, to do some some form, to ask them some questions about how they feel, about how's their current mental status, without letting them know that this I'm currently evaluating their mental stress level. And I try to analyze the evaluation form before and after the test, and try to compare. And the test if that activity is could cause stress or not, based on the statistical test. And that's how we usually do in the set collection for stress in constrained environment. For the constrained environment, for live log one, I need the user to look back through the data every day. Maybe they record data from the morning to the evening, and at night we look back the data again, remembering what they are having, what event they are having during the day, and try to answer if it's stress or not. It is still subjective, but this is what we can do during the research, because we cannot make sure 100% that people are correct at that time.
I see. So, how do you ensure that there is no bias involved during these experiments?
So the bias, there will be always the bias in this experiment, but the bias will be included in the experiment result. As you can see, that it dropped from the constrained environment result from the constrained one. The accuracy drops significantly. So this means that there's still a bias in evaluating if a person is stressed or not. But however, in case that we have more data to train, we have more evaluation form and evaluation method to evaluate if then really stressed or not. Then I think that we can do it, because my data is still small. It's only around 6 days, so it might contain false information, false data. But in case if it is large data, much larger, then the bias will be reduced.
Another question, how huge is the data set?
Sorry?
What is the size of the data set that you use?
Normally for a constrained environment, the data set only contain around 10 to 15 people. It's not many, because the wearable device that captures the signals in real time is quite expensive. So not many people or many researchers do that one. And they usually do in a very small room to test if it is possible to do it or not.
And in that case, what is the train test split for the data that you use for training?
You will split the train test based on, how can I say, there will be another method for you to split the train test in order to avoid bias. For example, you can record stress sessions in the first step, and then you record another relaxed stress session in maybe another day, and you use the previous day and the train and the rest test to avoid bias. In case that you accidentally use the train data that you extracted, for example. So in case you need more information, I can provide you my thesis. So I also mentioned the train test split, and also how can you train those models.
So we'll be interested in Thanks.
Yes, thank you, speaker again. Okay, it's 8 o'clock. We're out of time again, and we always tend to go to the very end. Thank you everybody for coming. Really appreciate it. We're going to go again in about 6 weeks' time. Probably only one before Christmas, given the time frame, but let's see. And we'll put up details on the meetup as soon as we can. You're very welcome. Please come along. Look forward to seeing you again. Thank you.
Thank you.
Uh-oh.
Dean has COVID.